So right now we're going to go ahead and continue talking about instantaneous versus average. And in this case we're going to talk about instantaneous velocity versus average velocity. We often have to distinguish between these two during times that we're working equations, and we need to know what they mean. Instantaneous means that it's the velocity at that instant. Alright, so it's at the instant. Instantaneous, instant. And average velocity is the velocity of the object over the entire period of motion. Whenever we use the calculation or the velocity equation where velocity equals displacement divided by time, this actually tells us our average velocity. It does not tell us our instantaneous velocity, which makes this the wrong velocity when we start talking about our acceleration. When we use the acceleration equation, we have to look at those instantaneous velocities, and the two important instantaneous velocities that we need to know about right now are our final velocity and our initial velocities. Those are instantaneous velocities. So the kinematic equations that we're going to use to solve word problems based on, motion and kinematics are going to be these four. Now this first one is just a rearranged version of the acceleration equation, where I get my final velocity equals my initial velocity plus acceleration times time. And the second one is going to be my displacement equals my initial velocity times time plus 1/2 times my acceleration times time squared. The third one is my final velocity squared equals my initial velocity squared plus 2 times my acceleration times my displacement. And then the fourth one down here says my displacement is going to be the product of my average velocity, which is how I find average if all I know is instantaneous. More importantly, initial plus final divided by 2. I have two quantities and I divide by 2. That tells me my average velocity, and then I multiply that by time and it gives me my displacement. Now, we're going to work an example problem because it's confusing whenever we have four different equations to choose from. Which one are we going to pick to use? So I've got these four here, and we have a word problem. If you follow my method for eliminating equations, picking the right equation is actually quite simple. So let me open up something to draw on. Here we go. And the first thing we need to do whenever we start picking equations is write down the knowns and the unknowns from the problem. So the problem states that a car accelerates uniformly in a straight line from rest at a rate of 2.3 meters per second squared south. What is the velocity after it has traveled 55 meters? Well, if I were to follow this through and pick out all of the knowns, this 55 has this little m next to it. Well, that tells me that that is going to be a displacement. So S equals 55 meters. And those are 2.5. Sorry, I don't know why my pen did that. And then as I read along, we have this number right here. And this meters per second squared tells me that that's got to be an acceleration. So my acceleration equals 2.3 meters second to the negative 2, and this is south. Okay. And there's something else that I know just from the words. So those are the two numbers, but from the words it says it starts from rest. All right, and so from rest, and because it's from, that's going to be my initial velocity equals 0. Alright, so that is everything that I can pull out of this problem, but now I have to write down, well, what do I want to know? Well, I want to know my final velocity, so that's V, is going to be my question mark. So the first thing that I need to do whenever I go to pick my equations after I write out these knowns and unknowns is I need to look at the equations and eliminate all the ones that do not have the unknown that I'm looking for. So if I look here at the first equation, yes, it has my final velocity in it. The second equation does not have a final velocity, so it is worthless to me right now. The third equation does, right there, and the fourth equation does right there. Once I've eliminated all the equations that I can based on my unknown or what I'm looking for, well, now I have to start looking at, well, what do I know? All right. So far, so good. We're down to 3 out of 4, and we'll go ahead and eliminate 2 more of those looking at my knowns. I look at the equation and I say, okay, do I know everything in this equation except for the unknown? So if I look at the first equation here, I know I want to know my final velocity. I know my initial velocity, I know my acceleration, but I don't know my time. Okay, so that proves a big problem. There's two unknowns in that equation, and so that one isn't going to work. And if I look at the fourth one also has time right here, and so that one's not going to work. And if I look here at my third one, on the other hand, well, I have my final velocity squared equals my initial velocity squared, which I know, plus 2 times my acceleration, which I know, times my displacement, which I know. So I know everything except for the unknown in this third equation. So this is going to be the equation that I am going to pick. So now it's just a matter of pulling it out and plugging in my knowns. So my final velocity squared, which is what I'm looking for, equals my initial velocity squared, so that's 0 squared, plus 2 times my acceleration, which is 2.3, times my displacement, which is 55. Now this will tell me that velocity squared equals 2530. And so I have to take the square root of both sides, so my velocity, or my final velocity, equals the square root of 2530, which is 50, comes out to be 50.3. Okay, so now we know roughly what my final velocity is, but we have to look at significant digits. Well, how many significant digits do I have here in the 55? The answer is 2. 2.3, I have 2. This 2, on the other hand, has infinite because it is part of the equation. We know that 2 to be exactly 2. So I need to have 2 significant digits. So my final velocity, V final, or V, equals 50, and the units are ms to the minus 1. But we're not done yet. We have to give it the direction. Now the acceleration, it starts from rest, and then it travels south. So let's say we're sitting here, and then we travel south. Right, and then I travel south. So that means my velocity is in the south direction. So it's 50.0 meters per second to the negative 1 south. Or just meters per second. So there is the final velocity. So I can go ahead and erase this question mark, and we'll go ahead and fill this in. So V final equals 50 meters per second south. Alright, good. Let's go ahead and erase. I gotta erase all this stuff. Alright, we also want to reset our equations because we want to pick out the equation that we're going to use now. So now the second question says, how long does it take the car to travel 55 meters? Now this how long, we sometimes can use long for lengths, but we also use long for time. So we want to know our t. How much time does it take? So now I'm go back and I start my equations over with. This one has a time. This equation has a time. Uh-oh, that one does not have a time. All right, so that one's gone. This fourth one has the time, and so we're good. We've eliminated 1 out of the 4. So now let's look at what we know and what we don't know. I know my final velocity. I know my initial velocity. I know my acceleration, and I'm looking for time. That's great, but here's the problem with using this equation. This is a calculated. My final velocity is something I've already calculated, but what if I calculated it wrong? If I calculated my final velocity to be wrong, then that's going to make my time automatically wrong. So let's see if there's another equation that doesn't include the final velocity, but includes the time. So if I look at this second equation, I have displacement, which I know, my initial velocity, which I know, plus my acceleration, which I know, and then the time is the only thing I don't know. So this is the preferred equation. Now, it's a lot harder than the other equation, and I'm not going to tell you can't use the first equation, but it depends on your level of confidence in your answer to begin with. They will both come out to be the same answer. The only problem is there's a level of uncertainty in whether or not you were correct with your final velocity. So I like to use the ones that I do know, the ones that were given to me in the problem. So if I look here, my displacement equals ut plus 1/2 AT squared. Okay, well that's good. This u is 0, so that whole term goes away. And so I'm going to get my displacement equals 1/2 AT squared. And that's a squared. And so now I want to rearrange for my time. And so to get this half over to the other side, I'm going to multiply both sides by 2, so that's 2s. And then to get my acceleration over, I'm going to divide by a. And that's going to give me t squared. Let's go ahead and square root both sides. And it eliminates that square for me. And then now it's just a matter of plugging in my information. So I am going to have the square root of 2 times 55 all over my acceleration, which is 2.3. And I'm going to go ahead and type that into my calculator. So 2 times 55 divided by 2.3, and then the square root of the answer. Now this tells me that it is 6.915. Alright, so now I have to look at my significant digits. This 55 has 2 significant digits. This 2.3 has 2 significant digits. The 2 has infinite because it comes from that half, which was part of the equation. And so I'm allowed to have 2 significant digits. This is going to be 6.9, and the units are going to be seconds. Alright, so there's example 4 complete. Let's move on. Now gravity is a very easy acceleration to work with. We're actually going to do a lot of experiments with gravity. So gravity produces a constant acceleration, but it depends on the celestial body that you're at. So either you're on the Earth, if you're on the Moon, if you're on Mars, if you're out in space. It also depends your elevation. It does vary a little bit here on the Earth, but not very much. And so we'll just assume that it's constant throughout the whole Earth. It acts on an object when it's in free fall, and it always points down. Alright, so it's always pointing down, which makes it nice when we do our calculations. We give it the variable g, and for this class we'll use g equals to 9.81 meters per second squared. Now if you're an engineer, you'll probably use 10 meters per second squared. You can also use 9.8, but let's just keep it at 9.81 so we keep the significant digits. So now we have a couple example problems. So let's go ahead and pull out something to write on so that we can go ahead and fill this out. And we'll erase everything. So we have a rock dropped off a school building and it hits the ground 4.6 seconds later. How tall is the school building? So here's my school building. Let's go ahead and draw a picture. And I drop a rock. Splat. Okay, good. So I want to know how tall is it. So assuming that we drop it off the school building, right level with the height, and we time how long it takes, well, we can figure out the height. So the time equals 4.6 seconds, and the acceleration equals 9.81 meters per second squared, and this goes down, just so we know it goes down. Now, whenever I drop something, whenever I first let it go, we assume that its initial velocity u is going to be 0, because for an instant it's at rest before gravity starts pulling it down, before it starts accelerating it. And then the final thing that I want to know is I want to know this y, or the s, the displacement of the rock. So we'll go ahead and use the term s. That's my question mark. So let's go through our equations again, and let's figure out which equations to use. All right, so I'm looking for s. Well, this first one does not have an s, but these other three do. Okay. So now let's go ahead and look at our knowns. Do I know the time? Yes. Do I know the acceleration? Yes. Do I know my initial velocity? Yes. So I know this one. Let's check the other ones. Do I know my final velocity? Do I know my final velocity? Good. So now we have the equation that we're going to use, and that is s equals initial velocity times time plus 1/2 AT squared. And seeing how S is what I'm looking for and it's already solved for, I don't have to do any rearranging. Another thing that I can note is that this term will go to 0 because my initial velocity is 0, so 0 times anything is 0. So S is going to equal 1/2 AT squared. And so I'm going to go ahead and fill that in. 1/2. Now my acceleration is pointing down, and so we usually use the convention that right and up is positive and left and down is negative. And so because this is going down, we're going to go ahead and give it the negative 9.81 meters per second squared. And then my time, which is 4.6 seconds squared. So now let's go ahead and type this into the calculator. 0.5 times 9.81 negative times 4.6 squared. And that's going to give me my S to be 103.789, and that's negative. So this tells me the displacement of the rock is 103 meters. Wow, that's a tall school building. But let's see here. We have 3 significant digits here. All right, so we're not done yet, and we have 2 here. So the least amount is 2, and so that means I'm allowed to keep 2. So S is going to be a negative 1.0 times 10 squared, and this is going to be in meters. Now this negative sign tells me that the rock falls down, but we want to know how tall is the building. Well, we usually measure the building from the ground up. So we're going to say the building is, the height of the building is going to equal 1.0 times 10 squared meters. All right. Notice how I put it in scientific notation to show that I have 2 significant digits, but I still keep the 100. All right, let's go ahead and move on to the next problem. Clear this one. All right, this is the last example, and we're going to look at, we have a rock that's thrown up from a cliff with an initial velocity of 3 meters per second. If it takes 4 seconds to strike the ground, how high is the cliff, and how fast is the rock moving when it hits the ground? So let's open this back up. Write down our knowns, and so we have our initial velocity u equals 3 meters per second, and it's up. Okay, it takes 4 seconds, so that's going to be time. And I know this says 3. Let's go ahead and cross that out, and I'm going to tell you it's 3 ms to the minus 1. That's my bad. So 3.0. That gives us 2 significant digits. And we want to know how high is the cliff. So this is going to be that S. And we want to know how its velocity when we hit the ground. So let's break this down into 2-part questions. We know that G equals negative 9.81 meters per second to the negative 2. And so that means it's just 9.81 meters per second squared down. And so I'm going to go through here and I'm looking for S. No S. The rest have S's. No displacements. The rest have displacements, I mean. And then I look at, well, I know the time. Here I don't know the final velocity. I don't know that. So these two are out. So I know everything in this equation, but I'm looking for S again. And so S equals U, or my initial velocity times my time, plus half AT squared. And so I do have an initial velocity now, which is 3.0. And my time is 4.0 plus 1/2. Now in this case, negative 9.81, because it goes down, times 4.0 squared. All right. Now we just have to type this into our calculator. So let's do this in 2 steps. 3 times 4 is 12. plus, well, 1/2 times negative 9.81 times 4 squared. Well, that's 16. Half of 16 is going to be 8 times 9.81, which is going to give me 78.48. And because of that negative sign right there, it's going to be a negative. So that means that my total displacement of the rock is going to be 12 minus 78.8. I'm sorry, it should be 78.48, which tells me that it's negative 66.48. And then if I look at my significant digits, I have 2, I have 3, I have 2, I have 2, and so I can only keep 2, and so this is going to be negative 66 meters. Now, once again, it asks me how high is the cliff? Well, the cliff, it has height, h, equals 66 meters, because once again we measure it from the bottom up. Alright, so now we have that. Let's go ahead and work on the second part of the problem. We're going to go ahead and reset our equations. And so now I want to know its velocity. So I know its displacement is negative 66 meters, but let's talk about its velocity. Do I know its initial velocity? Do I know the time? Do I know the acceleration? Yes, I know all of those. See how great that is? First one. Now, I calculated the displacement, so I don't like to use displacement in my equations because, well, what if I got it wrong? Once again, let's use something that the problem tells us all of our answers. And so we want to know our final velocity, v. And so our initial velocity, u, is 3.0. All right, and that goes up, plus my acceleration, which is negative 9.81 because it goes down, times my time, which is 4.0. And let's do the math. So I type this into my calculator. I get 3.0 minus 9.81 times 4.0. And that's going to give me a negative 36.24. Now, once again, I have to look at significant digits, and so my final velocity is, well, I have 3, I have 2, I have 2, and so I can only keep 2, negative 36 meters per second to the negative 1. Now, this is absolutely correct the way that it is. The negative sign tells me that it goes down. You could also rewrite this as 36 meters per second down. Right? You can also include, or just include, the arrow pointing down. You cannot have this direction down and still have that negative sign because the negative means the opposite. And so if you put the negative there, well, then that's going to be 30 meters per second, the opposite of down, which is up. So choose whichever one and stick with it. Okay? I prefer to have the direction and not the negative sign, but they both are correct.